All right, good afternoon, everybody. This is Steve Wilson from the State Water Survey. And today our webinar is entitled Groundwater and Well Construction 101. Thanks for attending. I want to mention that the private well class, our program sponsored, funded, and supported by the Rural Community Assistance Partnership through funding from US EPA. And the work that we do online, they have folks, boots on the ground, able to support well owners and professionals that work with them all over the country. Okay, try to do this so my webcam doesn't kick on here. Okay, this webinar is part of our national program through the private well class to support well owners. The materials follow our online class. I do want to mention this is not the online class that's, private well class. That is a 10-lesson self-paced course that you sign up for and you receive through your email. And if you haven't participated in that, it's all free. And I'll talk about that a little bit later, but it's really worth your while to go through those materials. And there were a number of questions that you all asked in advance that are directly answered in those lessons that we probably won't get to today. There's 490 people who registered and well over 100 questions, I think. So we'll answer a number of those, but not all. And one thing I will mention is that there is time at the end. We'll stay and answer questions as long as you all want to stay on. This webinar is meant to end at 3 Central Time, but if we get follow-up questions, we will keep answering those as we go. So if something comes up during the webinar today and you have a question about it, just put it in the chat or the question box on your GoToWebinar screen. Katie Buckley, who's with me here today, will keep track of those and we'll go through them at the end. There are 2 handouts. If you are looking for CEUs or CEs, there's a handout tab on your GoToWebinar screen, so download those. And yeah, we'll talk more about CEs here in a second. I think the next slide. Yeah, so we provide CEs, continuing education, for NEHA, the National Environmental Health Association, whether you're a NEHA member or not. If your state accepts NEHA CEs for credit, you can get those by participating in this webinar. If you are a NEHA member and go through their credentialing, then you can only take this particular class once every 2 years, depending on when your credentialing cycle starts and ends. And so if your credentialing cycle just ended on 4/30, so it started 5/1/22, and you take this today, you can't take the same class, Groundwater and Wells 101, until after 5/1/24. And I've listed in the bottom right over here when we've offered this particular class before. And you can email us at info@privatewellclass.org for a copy of the slides if you're in a different state or you have different kind of credentialing, a certificate of attendance, and any other information you might need. We're also an Illinois LEHP provider, and just Illinois, and that's we're here in Champaign-Urbana, Illinois, at the University of Illinois, and so we support our county health departments and work with them a lot on a number of things, even not related to this particular project. So we try to support their efforts as well. So I mentioned Katie Buckley. She's our water resources outreach specialist and works on the private well class and our wateroperator.org programs. And I'm Steve Wilson. I'm a groundwater hydrologist. And Walt Kelly, who's the head of the groundwater section here at the Water Survey, has a geochemistry degree and is very helpful in answering some of the particular questions you all have asked. And we kind of tag team those beforehand and add them to the slide deck. So you'll see that at the end today. I do want to mention, we're funded through Rural Community Assistance Partnership. They get a grant from EPA. They're made up of 6 regional nonprofits. They each have their own name and do their own work outside of this particular grant program, but together we all offer kind of a tandem effort to support well owners. And so there's a lead in each of those 6 regions, and to do well assessments on individual wells, help other professionals put on workshops, provide speakers. There's a lot of activities related to private well work that they'd be glad to help you out with. And you can contact us, or their names are on the side there with a phone number and an email or a website. But if you contact me, I will get you in touch with the right person depending on what state you're in. And the well assessment program, it's like a sanitary survey. I think I have that next. This is just the front page of it. It's a fillable PDF. It's a 18-section assessment, one-on-one with the well owner. So if you have a problem well, they'll come out and meet with the individual well owner and complete this, and it only is shared with the well owner and with us. And it gives the RCAP person a chance to explain issues related to the well, if there are any concerns, and in most cases they can collect a water sample. And so it's a really great program in that it really, the way I look at it is we're reaching well owners one at a time, but they've done over 3,000 of these already. And in a lot of cases, they're wells where there's actually an identified issue, and they come in and try to identify why that has happened, what they can do to change it, that sort of thing. As I mentioned, it's like a sanitary survey. It's also a chance to really educate well owners about their specific situation. If you've worked with very many private wells in your past, you know that almost everyone is different in some way, and it really doesn't promote best practices and encourage communication. And it gives a well owner a chance one-on-one to ask a professional questions where they're not trying to sell them anything. They're just trying to provide answers and help them understand their well better. I need to update this, so it's over 3,000 now. We also did a bunch of workshops a few years ago where we taught folks how to use this assessment tool, and we actually do that now here at the private well class. Once or twice a year, we'll hold a 4-hour online workshop to talk about outreach and some of the things we learned from some work we did for CDC on why well owners don't test, as well as go through some examples of how to use the assessment tool to get at problems with wells and how to reach well owners who may have an older well or don't have the knowledge they need to have in order to be a good steward of their well and their water supply. So quickly, a little bit about the State Water Survey. We're a really unique agency. We're a sister agency to our State Geological Survey. We're on the campus of the U of I, but we're the only water survey in the country. I think Oklahoma may have started one a number of years back, but we were started because of cholera and typhoid outbreaks. And so we've been dealing with public health and water quality since then. A lot of engineering, developing groundwater models, looking at water quality. We have a lab that until 2008 offered free water analysis to any well owner in Illinois. State budget problems changed all that. But we also house all the state's well logs. And so in our files, going back that far, there's a lot of really cool information I've been lucky enough to be involved in going through. Just looking at things like, when a filter plant was installed in Quincy, how it changed the typhoid rates going back before 1900. And this is an investigation of a typhoid outbreak in Rockford, Illinois. They went so far as to investigate if it could have been the milk. And E. Erickson had a dairy route. And obviously, this shows that by September, there were 112 cases, and the dairy route only had 7 or 8 of those. So that wasn't the case. But this is an old glass plate slide that's in our files that dates to 1913. So there's a lot of cool history we have, and I guess I'm kind of proud of all that. But even things like, when Illinois passed a law that banned using these common cups, that's actually on the books in Illinois, and you can see that tin cup in the foreground in front of the wood floor on the well cover. But this is a public park, and the water survey is there to collect a sample. I don't know what year this is, but judging by the cars, it's pretty darn old. So a lot of cool history. And this is, Weldon's a small town in central Illinois. Drill rigs look a lot different today. Just like I said, there's just a lot of cool history. So getting on to what we're here to talk about today. The things to remember if you're a private well owner are that, they're not regulated. Once they're installed, it's really up to you as the owner and the user to be sure your water's safe to drink, and that you can't go by taste, smell, things like, people complain, a lot of people have problems with sulfur, that sulfur smell, that rotten egg smell. It's not necessarily dangerous, just like iron stains everything and it's not necessarily dangerous. But many things that are dangerous, like arsenic, are colorless, odorless, and tasteless. So you can't judge your water by how it looks, smells, or tastes. You really have to sample. And I grew up on an old dug well that was not safe. When it rained hard, we had cloudy water. Now I live in town on a community water supply, and you pay here $40, $50 a month, and that's the cost spread out over the 150,000 residents for sampling, maintenance of our water lines, all the infrastructure, having someone who tests the water regularly and who meets all the conditions of the Safe Drinking Water Act, to ensure that the water, when I turn on my tap at home, the water's safe, and that's your responsibility as a well owner. The best way you can look at it is that you're the water operator for a very small water system, your family's, and take it that seriously. And so that's really the take-home message. And what we hope you get out of not only this webinar, but our program, is that you learn more about your well so that you understand where your water is coming from. Is it a sand and gravel well or a bedrock well? How deep is the pump set? If is the pump in your basement, or is it down in the well? Is it submersible? Do you have a screen or not? All those things, as well as who you can talk to locally to find out if there's naturally occurring contaminants, like arsenic is a common element in the Earth's crust. And so we see a lot of areas around the country where there's naturally occurring arsenic, and it's just the way it is. But you need to know if it's there. Other areas may have things like uranium or radium. And so I'll talk more about that as well as we move through today. But the point of our class is to give you enough information to understand your well and how it works, your geology and how it works, how water gets into your well, so that when you have a problem or you have a question, you can ask the right questions and not questions that really indicate that you are brand new to a well and have no idea how to take care of it. And lastly, sampling your well is the most important thing you can do. Even if you have a properly constructed well and it's there's no natural contaminants, all those things, sampling your well just ensures that you know what's going on with your water quality. So a little bit of a kind of geology lesson and how aquifers work. So pretend this square is a jar of sand. So water, if you pour water into that jar of sand, water is going to go in through all the air spaces in those grains and fill it up. And that's what happens in an aquifer. You have a sand and gravel aquifer. It's a porous system. So water can move through all of those sand grains just like it would in a jar. And so the porosity is a measure of the volume of the actual pore space or air space between all those grains versus the total volume of that square or that box there. And typically in a uniform sand, we'll have a porosity of close to 30%. And what that means is that if you're in a sand and gravel aquifer, your well is, and it's 100 feet thick and it's fully saturated, has water in throughout the whole 100 feet. If you took all the sand away, you'd still have 30 feet of water below ground. So they're very prolific when they're large sand and gravel aquifers like that, because water can move through them so easily. And so you see a lot of areas like along river bottoms where there's irrigation and they're pumping 12, 15, 1,800 gallons a minute. And they don't see a whole lot of drawdown because water can move to the well quickly and there's just a lot of water available. The other side of that is a bedrock system, which is fractured rock. So water doesn't flow through rock. It can flow through some sandstones minimally and store a little water, but most rock, it's solid rock. It's the fractures in the rock that actually provide the water. So when you pump a well that's and it's a bedrock well, it's open to those fractures. And so water's moving through those fractures, kind of like pipe flow. And it depends on how many connections there are between the fractures and how many fractures your well bore hits when it was drilled, how much water you might have available. And you can see, we see irrigation wells in fractured bedrock, and we also see wells that are 600 feet deep and only pump maybe a gallon a minute because there just aren't many fractures and there's not a water available that way. Just some examples here. For porous material, the top three, they can be well sorted or poorly sorted. So what happens if it's poorly sorted, and this is actually, I took this from a well owner handbook from the University of Arizona, but it's typically uniform sand has more porosity than poorly sorted sand because all the smaller particles end up getting in the middle between the bigger particles and kind of clogging it up, if you will. And so a lot of times a poorly sorted sand will have a porosity that's less, maybe 20% or so, versus the bottom three are all fractured rock. And granite, the middle one there, is kind of the basement rock. It's even so in Illinois we have you can run into sandstone and dolomitic limestone, lots of things, but eventually you hit granite. And so like in the Rockies in Colorado, there's a lot of granite near the surface because of the mountains. And so granite is very unfractured, I guess would be the best way to say it. A lot of times the porosity of a bedrock that's granite may be 1%. And that means there's only 1% of pore space in that square. Versus caverns and limestone, when you think about Southern Illinois, Indiana, Kentucky, Tennessee, other places that have caves and large caverns, karst topography, those are water dissolved openings. So those fractures are continually getting a little bigger. And over time, with water flow, like especially when the glaciers melted, a lot of big caves were formed. And so those store a lot of water. They also are connected to the surface in a lot of cases. And you can have direct runoff from the surface get down in those areas. If you've lived in one of those areas, ever been there and saw sinkholes, that's what those are. That's where the rock is kind of dissolved away, and so there's a sinkhole at the surface, and things can go directly in to the aquifer. So that was porosity. That's a measure of the volume of space available to have water in it. And the other measure is permeability, which you can kind of think of as a velocity. So a highly permeable gravel, water might flow up to 3,000 feet a day. As the grains get smaller and the water molecules have to, kind of make their way around, you get down to silt and clay, then water moves very slowly. And especially clay is considered an Aquitards, so is silt really. It only moves, you can see here, as little as 1 foot in 10,000 years in a really tight clay. So it doesn't allow water movement, and that's important because when you start pumping your well, the water level lowers in your well as you take water out, and then that has to fill back in from all the surrounding aquifer material. And how fast your well can fill back in so that you can pump more is totally dependent on how quickly water can get back to your well. And so in a gravel or sand, that's pretty fast, and a lot of times you can pump a lot of water, and that's on the unconsolidated side where you have sands and gravels. On the bedrock side, we have limestone, sandstone, shale, and just rock. You can see that as long as you're in fractures, water can move pretty a lot, 3 feet a day, even more than that if you're in some major fracture features of a limestone or a sandstone. A lot of community water supplies. Something just happened. Katie, are you still there?
Yep, it looks like maybe your presentation crashed there. Can you open it back up?
Wow, I don't know that I've had that happen before. I apologize. How interesting is that? Okay, let's get to our... 119. Okay, we're here, right? Well, yeah, how about that? Interesting. We'll see. Hopefully that doesn't happen again. Interesting. So we were talking about permeability and how fast water can move through. If it's a large fracture, water moves through like it's free flowing, like through a cavern. But typically, when you start looking at things like shale, shale is really cemented clay, and so it can move as little as 1 foot in 100,000 years. And so what we typically see in bedrock is you have units as you move down, geologic units, and you go through one, and so you might have a sandstone or a limestone, and then a shale, and then another limestone or some other type of formation that holds water or is fractured. And the shale acts as an aquitard and separates these layers. And we see in deeper wells, a lot of times we see that if you're open to both of those, you can actually influence the water quality from one aquifer to another, because the well bore acts as a connection. And you might hit a layer that's salt water, and you can affect the water quality of your well because you went into a unit that actually has poor water quality. But it's really about how fast water moves, and that's what permeability means. It's kind of, as I mentioned, the velocity. And so you have units that transmit more water that are considered aquifers, and units that prevent water from moving, like clay and shale, that are considered aquitards or aquicludes. So this is just a simple example to show. I always say this, like if this was a horse tank and it was full of sand and gravel, the upper left, and you poured water evenly across the top of it, that's kind of the wetting front that you're looking at, as water's moving down through it, versus the other options. If you have water at the top, the dolomite, it looks like bricks in this image. Those are meant to be fractures, and those are uniform fractures that you don't normally see. Crystalline bedrock is more like granite, and they're small fractures and they're very unconnected. So it's really iffy how much water you can get out of those type of units. And then the sandstone and dolomite together is more of a realistic example of how things work. Water can move through the sandstone, as I mentioned. It's cemented sand in a way. Then it gets to a dolomite layer, and there's no shale in this, but in the real world, it's much more complicated. And usually these bedrock units are not flat straight across; they're at an angle, and so it depends on where you're at. In one place, the aquifer may be near land surface, and 30 miles away, it may be at 1,600 feet because of the angle of the rock in the ground. It's not flat. Here's another good example of how that works. So if you're in Iowa, which they've got glacial drift, there were glaciers, you have some sand and gravel aquifers at the top and wells in those sand and gravels. And the one really short well there near the little river, and that's that large sand and gravel unit that looks like its own riverbed was the river when glaciers were melting several 100,000 years ago. And then as those receded and the glaciers went away, that all filled up with sand. And those are very prolific aquifers that a lot of folks use along river bottoms. I know, yeah. And then as you move through, you see these units: limestone, shale, limestone, sandstone, and shale. And again, the shale acts as an aquiclude. It doesn't let water through very fast. And so it's not considered, it's a confining layer, and it doesn't let water through. And this is more of an example of what you'd see in the upper Midwest, Illinois as well, of what we have. And, if you have a good sand and gravel aquifer, like we do in Champaign County where I live, most wells stop there. There's no reason to drill deeper. If you find a water supply and the water is drinkable and safe. And so deeper wells usually go in when there is no shallower source. So I apologize. Boy, we need to redo this figure. It's very blurry, as I notice. This is really this is meant to show how water flows. So water is part of the hydrologic cycle, right? Our groundwater is part of the hydrologic cycle. And so the typical cycle you see is it rains, it runs off to a stream, ends up in the ocean, and then it evaporates and starts all over again. But some of that water infiltrates. That's why you have a water table. and it recharges into the ground, and it slowly moves through an Aquitard, it could be, or an aquifer. Some of it will seep out and go into a stream. Some of it will continue to move down, and it can take centuries or even millennia for water to, the same water drop, that if you're following it, it can go in a number of different ways. These arrows show how eventually the water all ends up in the stream, except for the bottom lower confined aquifer, where it's moving towards a different discharge point somewhere. But groundwater does discharge. It may take tens to hundreds of thousands of years in some cases, but it does. And so it's constantly moving. The water that's near your well today will be down gradient in a few days, moving towards some discharge point like a stream or a river or a lake. And so it's a continually moving process. That's why when you hear about plume of contamination, it's because the groundwater is always moving. So if something gets spilled, it's going to move towards some discharge point. And whether it makes it there or not, or whether it gets broken down before it does or whatever, there is always constant water movement. It's not just sitting still down there waiting for you to pump it. So a little bit about aquifers and wells. There's three types of wells the way we define it. There's dug and bored wells, which are large diameter, and typically you put a well, a dug or bored well in because there is no aquifer or it's too deep. I grew up on a hand dug well. It's 3 foot diameter. It's only 14 feet deep. My grandpa hand dug it in 1933. He didn't realize that 80 feet down is a sand and gravel aquifer at the time. And so we had this old dug and bored well. But if you know there's an aquifer, you might you'll drill a well, and either into sand and gravel or into bedrock. And so it depends. Sometimes you have choices. There may be 2 or 3. Like it may be that the shallow sand, if it's too shallow, it may be a risk for surface contamination, so you drill deeper, or your driller may have reasons for explain that to you about why you might want to drill into this aquifer instead of that one. But it's up to you to understand the geology and the differences, or talk to someone that's independent, which would be like your state geological survey or your USGS office or your water resource agency in your state. So we're going to go through these. So these are all dug and bored wells. The one on the upper left is a hand dug well that is, it's actually in a cattle pasture. That's why those posts look so different. It's because they've been rubbed as scratching posts for cattle. So you also have cattle doing their business there. And, it's covered by some 2x10s and pieces of tin with concrete blocks. Snakes, rats, a lot of smaller creatures can probably get in that well. And if they fall in it, they're going to die in there. We've pulled a lot of things out of wells that shouldn't be in there. It's a bacteria problem. It becomes a smell and taste problem. It's unhealthy. And a lot of these still exist. It's just how it is. And a lot of people don't see that there's a need not to have a protected well at the surface. The one on the right so it looks like concrete tile going vertically, and that's exactly what it is. Those are 4 foot sections of tile, and they go down to whatever depth, but where the male threads and the female threads fit together, or the seam, it's not cemented, so water can seep in every 4 feet. And this one has a 3 foot concrete cap that you need a pry bar to pull that off, and then to get into the well. And the one on the bottom left is just like the one on the right, except that the 3 foot tile doesn't start until 10 feet down. And that concrete pad has a hole in the top of it for that steel casing, or that casing there. And so it looks like a drilled well, but it's actually not. It's a large diameter well that was bored by a boring machine. So these are those 2 installations, the 2 that are actually bored. You can see it's 36-inch diameter concrete tile. Usually you put either concrete or some kind of fill that would be clayey, so that it's so water doesn't transmit through it very easily on the upper 10 feet, so that you're protecting it from surface contamination. But then further down, water seeps in from this geologic material that shows sand lenses and a lot of clay. And so the deal here is, the reason you have a large diameter well that's 3 foot or 4 foot, we've seen them as large as 20-foot diameter, someone did by themselves, is so that they'll store water. So there may only be 20 feet of water in this well, and when you pump it in the morning, there's so little water that can recharge. It doesn't recharge very quickly, and so you may pump it down 10 feet, and then when you leave for the day, it slowly seeps back in, and it provides that storage like a cistern would, so that you have water when you need it. And so, there's sand around, the borehole's larger than 3 foot, so you can put the 3 foot tile in, and then you put sand down around the casing to give it a little more volume around those tile. And so that's what you're seeing in those two images. And the one on the right is really just meant to be a better example of how to protect from surface influence for your well. Because if you don't put the concrete on the one on the left, and you don't have anything particular there to protect it, like the picture we just looked at, let's say that concrete tile stuck up 1 foot. That means there's a seam 3 foot below ground surface. That's pretty shallow. There's going to be a surface infiltration that gets to that. And so if you haven't sealed around there, you're going to have possibly some surface influence in your water. So sand and gravel wells, this is a well screen. And it's really just like a screen on your door. A screen on your door lets the air through and keeps the bugs out. A screen on a well lets the water through and keeps the sand out. These are in sand and gravel wells. They're usually, the casing can be PVC or steel, but usually the screen is woven stainless steel, not always. We have monitoring wells that we use PVC screens, but they're not being used for drinking water, and that would not meet code in most states. So the driller drills into sand and gravel. He's collecting samples of the aquifer material as it comes up, and he's using that size of those grains, whether they're gravel or sand or fine sand, to size the screen so that it'll keep most of the sand out. And then the other thing you do is you put a gravel pack of uniform size sand around the screen that'll help trap all the fine sand and not allow it to get to the screen. And it acts as a filter, if you will, for those. And it also makes it easier for the water to get there and clean water. When your well starts pumping sand, it usually means there's a breach in your screen of some sort. That's a quick way to end your pump. They scour the inside of your pump. It won't be efficient. It could damage it. It could also damage your pipes in your home if you're getting sand in your home. And so the screen is there to keep from any of that happening. A lot of times when you start pumping sand from a sand and gravel well, you just have to abandon it and put in a new one. And so it's a bad thing. This is an example log. This is from Illinois, but I want to point out a few things. One, this is showing, if you look at number 18 on the bottom right, there's fine sand from 204 to 230, and then coarse sand from 230 to 240. So when you think about it, if you think about a stream and the sandbars that are along those, if it's big enough, if it's a river and has sandbars, when water's moving through, it's picking up the finest pieces of sand, and it's, the larger particles fall out first. So what you see in these buried sand and gravel aquifers is the bottom of the unit, of the geologic unit. So let's say the sand, in this case, goes from 204 to 240. The bottom has the largest particles, and the top has the finer particles, and that's exactly what we see here. And that's just the nature of how the velocity of the water and what it could pick up and what it couldn't. So the larger particles fall out first. So you're typically going to try to get to the bottom, or at least get to coarser sand, so that you have a large enough screen, between the woven pieces of a metal that water can freely flow through. And so that's what they've done here. It was fine sand, and then it got to be coarse sand, so they stopped and they put in a screen. It says screen diameter 4 inches, length 8 foot. This is number 14 I'm reading, and it was the casing and liner is 4-inch, 11-pound drive. That is a pipe type, a steel pipe type. It even has information about the pump. It was pumped at 15. It's a 15 gallon per minute pump, which is more than you need for most private wells. And then they show the static level, number 17, and the pumping level, which they didn't include here. But given that there's this much sand, I'm assuming the pumping level isn't much lower than the static level, maybe just a few feet at most, pumping at 15 gallons a minute. And so here the water level is actually up to 75 feet below land surface. So it's up in that blue gravelly compact clay that goes from 70 to 204. And that means that aquifer is under pressure. And so, I'll explain that in a little bit. But you should try to find your well log and understand what's in it. Go to your resource agency that houses these, or even a driller, and ask them to help you understand it if you can find it. The one issue I'll tell you now is in every state, there are many wells that are older, or there wasn't a log filed, or it was before well logs were required. And so you have about a 50-50 chance, unless you know the age of your well and it was pretty new, then you will find the log. So the third type is bedrock wells. And as I mentioned, a bedrock well takes advantage of the fractures in the rock. So if you look at this diagram, it shows the steel casing and it stops 10 to 20 feet into rock. So you seat the casing into the rock so that it's solid. And then the rest of this is after you've already drilled down, you might drill 200 more feet. But when you go to put the casing in the borehole, you only go in 10 to 20 feet into the rock, because the casing won't let water through, right? It's solid. And once you get past the casing, then the rock itself acts as the casing for the well. You drill a hole in a rock and you're hoping to hit fractures. And you can see this one does hit a few fractures down near the bottom, near the pump. And so that's where all the water is coming from. And so it's like pipe flow. And because of that, depending on how many fractures you hit, if you only happen to hit one fracture, all the water is going to come from that fracture, no matter where it goes. There's no way to know. It's buried. So it could run back to the surface. It could run, it could run to a river, all those things. But it just means that you need to sample, because a bedrock well can be influenced over a larger distance, especially if it's a low flow well. Here's a typical well log. This is actually a camp in Algonquin, Illinois. I pulled these from one of our records. What's interesting about this one is when you look at the geologic formations they pass through, they hit broken limestone at 187 to 189, which the very top of the bedrock is always broken and fractured more because it's more weathered. At one point was land surface. Glaciers came along and filled everything up above it, at least in this part of the country. So then they had 68 feet of limestone to 257, and then they hit hard gray shale. So they went through 3 feet of it and didn't get through it, and so they stopped. They must have realized there was enough water based on how the drilling was going and the water that they were pulling out with the cuttings, and so they stopped the well at 260. And so in this case, they put in PVC pipe to 179, which is 10 feet above you get to bedrock. And then they use black steel from 179 to 199. And that means they seated it 10 feet into the rock. They hit broken limestone at 187. They have a steel casing down to 199. So it's 12 feet. And then the rest of that, there is no casing. And yet there's an open hole down to 260. So the water's coming, there's a mistake on this log. The person who filled this out, since it's typed, did it in the office when they got back, and they're probably used to the last unit that's listed being the unit where the water's coming from. So they listed shale for number 12. From 257 to 260 is a water source. That's wrong. The actual water source is the limestone from 189 to 257. You can see here the static water level was only 130 feet below land surface. So again, water rose up in the well above the aquifer. And when they pumped it at 25 gallons a minute for 2 hours, it dropped to 160. And so typically what a driller will do is if they're going to put a 5 gallon a minute pump in your well when you're done, they might use a 15 gallon per minute pump and pump it for a few hours. And if they're checking static and pumping water level to make sure that the well doesn't go dry and that there's plenty of water still in the well, that tells them, it gives them an idea of your capacity, because you're not ever going to pump it at 15 gallons a minute if you're just a single home on a private well. It's going to be much less than that, and that's why they put a smaller pump in on a typical home well, residential well. But that's one way that they can use their own pump and over pump it, so to speak, and get an idea of how much it's going to use. So yeah, and so if you look at number 5, the pump they installed was a 12 gallon per minute pump. So they it only pumps half as much as what they did whenever they built the well. Okay, so there's lots of issues out there as far as, a lot more in the news today in the last 7 or 8 years than there used to be about private wells. But what it really comes down to is public health protection. So we're trying to protect the water so it's safe to drink and doesn't make us sick or cause long-term problems. It's also source water protection, which is the things we do around not only our well, but near where water recharges an aquifer is a huge issue. Whether a septic is causing a problem or livestock or ag chemicals or whatever it might be, and then just general water quality. And so those are the things we're really concerned about. There are a lot of other things that end up being in the news, drought, flooding. There's a lot going on with flooding these days, just because, the weather we've seen has been more extreme in the last, probably longer than this, but at least the last 10 or 15 years. And it's really starting to become more regular for it to be extreme. But contamination issues bring up a lot of newspaper articles and things like that. And even boil orders. We've had folks tell us, water operators tell us that, a boil order has nothing to do with a private well. If a community has a boil order, it's because they've had a main break in their water line. And by law, through the Safe Drinking Water Act, they have to maintain pressure in that line. So when they have a break, they lose that pressure, and that means things could get into the drinking water line for a public water supply. But I've had numerous water operators tell me that they get calls from private well owners in the area whenever they put a boil order in the paper or through Facebook or whatever. And it just goes to help explain that, you should know that that's not a private well issue. It's because of a public water supply. And so all these things in the news, though, for those of you that are not well owners, but you work with well owners, they're an opportunity to educate the well owners you work with. So, and there's other ways to handle things. I love this picture. This is actually a well out in the country. When I drive home to see my mom, this is near those trees are the edge of a small stream, and it's in a floodplain. And it's for a hog farm that's probably a third of a mile away uphill, so to speak, up the landscape. And so to prevent this well from being overtopped during a flooding event, they've actually have solid casing that's about 9 foot high. And so they've put this well, elevated the top of the well, which is a little bit of a pain if you think about it. If you had to pull the pump or whatever, you'd have to put something over that and have a pretty tall rig, but it prevents ever having issues with that being overtopped and floodwaters getting in if the gasket's not tight or the vent tube isn't correct or whatever. You don't have to worry. And so if you put a well in a low-lying area, I think it's a great idea. As far as all those other things, what it really comes down to, what we find, there's really two issues that affect most water quality issues in wells or contamination issues with wells. And that's poor well construction, wells that don't meet code today or aren't properly protected at the surface. This is just an example of two wells. We've done a lot of work with dug and bored wells in Illinois and done a lot of sampling. And, you know, there's many wells out there still that aren't properly constructed, even wells in pits, which, you know, used to be done before the invention of the pitless adapter so that pipes didn't freeze. You put your well in a pit below the frost line and you stopped it there and ran line into your house. Then you have to worry about your well freezing. But those pits are dangerous. They're not only a safety concern, but they can also be, you know, during a heavy rain event, they can fill up with water and then your well's flooded and all those sorts of things. And the other thing really is lack of well owner knowledge and education. We all need to do a better job of reaching out to the well owners we work with, helping them understand some of the basics of what being a well owner means. And we see many times we get questions that, you know, they may be new to the whole idea. They've always had city water. And it's a concept that takes some effort to learn about your well and how to take care of it and what all that means. So again, those are the two biggest issues we have. And if we could solve those two things, I think we'd eliminate about 90% of the water quality concerns with private wells. So going about correcting poor construction. So most states have well construction code, two don't. But even those codes have changed a lot. I know in Illinois, the first well construction code was in 1968, and it's been changed probably dozens of times as we've learned more about what works and doesn't work, what's safe and isn't. You know, materials change, all those sorts of things. But in every case, in every state that does have construction code, only new wells had to meet that. So you have wells that are before any kind of code, or maybe were from the original codes that maybe weren't as protective as they are today. And because they're all grandfathered in, we see all kinds of wells, especially in rural areas. You know, the well that I grew up on was hand dug in 1933. I mentioned it's still in use today, and it shouldn't be. It's just that simple. It's not safe. And we still see wells in pits, as I mentioned. And yeah, they're both a safety hazard and an opportunity for surface contamination. Here's just two examples. The picture on the left is from the Washington State Department of Ecology. They have a blog. They're the agency in Washington State that regulates well construction and drillers licensing. And so they have a blog where at least they did for a while, where they're putting information about extreme events that happen related to wells. And one of these here, you know, there's a piece of plywood over this corrugated pipe well, and the woman who lived there probably stepped on that hundreds of times, never did anything, never bothered her, never broke, never did whatever. And then one time it did, and it killed her. But if you look at this little well house, you see a funnel on there in the foreground that was probably used to put oil in the pump. There's a broom because of all the stuff that's fallen off on the sides. I'm guessing that gray stuff along the back is all old insulation that was on the walls. You know, anything can get in this well, rats, you name it, even if it's a building. It's just not how you want your water supply. In the picture on the right, that's a dead goat. And this is a well that was no longer used, but had been, what they'd done is this was an old stone well in southern Illinois, and they put a piece of concrete tile in it, and that stuck up about 1/2 foot. So somebody nearby, a nearby farmer had goats. One of his goats got out, curious, or because he was thirsty, fell in that. Nobody found it. And yeah, you know, we've pulled, like I said, we pulled frogs, rats, raccoons, a lot of things out of wells. And, you know, we've had people on our webinars who said, you know, my dad, we had this funny smell in our well, and we opened it up and there was like 50 snakes in the well. And they were drinking this water. And so it's, you know, you have to be diligent. You have to make sure your well can't allow those things to happen. And they do. So what should you do? If you can, bring it up to code, talk to your state agency that has well construction code. You're doing this voluntarily. They can't make you, but you want to do what's going to protect your well water from any kind of surface contamination or worse. So if it's a well in a pit, for instance, you can extend the pipe up to land surface and fill that in, and install a pitless adapter if you need to. So, you know, pitless adapter is a unit that fits in a well that allows you to basically elbow your pipe from your pump, your submersible pump, into your home at like 3 or 4 feet depth. And that's typically done when you have a frost line. So in a northern climate where you have freezing weather and there's a frost line in the soil every year. And so in some areas, you know, we see all the equipment out by the well, like the pressure tank and everything else, because it never freezes in some southern climates. And so it's a different, depending on where you live. But, you know, talk to the folks in your area that know how to fix those things, have them take a look, ask if there's anything wrong, especially about your well casing and making sure your well's properly protected at the surface. Same thing with abandoned wells. Since well logs weren't required to be filed until the 60s or 80s or even later in some states, there are many more wells that are out there that we don't have records for, and that's in every state, than there are wells that we do have on file. And, you know, as an example, Illinois passed a law in 1968, and I did a project where we were trying to identify all the wells in 9 rural townships. There ended up being 1,706 wells. And in our files, we only had logs for 788 of those, so less than half. And you have other states like New York where they didn't pass the rules to require a well log to be filed until 2000. And so they estimate they maybe have 10 to 15% of their well logs on file of the wells that are actually out there and in use. But many more of those old wells aren't even in use anymore. You know, the old house was tore down, someone, the son or whoever or daughter put a new house in, they decided to put in a new well. That old well just sits there, everybody forgets about it. And they're not only, again, a safety hazard, but also a source of contamination if they go down to the aquifer. Anything that gets spilled there or can get in it, or eventually, you know, that'll, depending on the type of casing it is, it will go bad. And so the best thing to do is to properly abandon and seal it, so that nothing can get in it and no one can get hurt. And the bottom line, especially these old large diameter wells, somebody gets on your property and whether they're supposed to be there or not, they fall in and it either kills them or hurts them in some way. You're probably going to be responsible in most jurisdictions. And so the best thing to do is, if you know you have an old well that's not being used, is to properly abandon it by sealing it. And you can talk to your local or state health authority about how to do that, or you can look it up online. Yeah, it's important to protect water quality. So yeah, here's some more examples. The 2 pictures on the left are both from that Washington State Department of Ecology blog. One, they're trying to get a horse out of an old well, and the other one, this guy in Shelton, Washington, fell. He was in his backyard, didn't even know the well was there. Fell 45 feet into the well. When they got him out, he walked away. He was very lucky. But then all these newspaper clippings were from a guy named Harry Hendrickson, who used to be the groundwater education coordinator in Illinois, had all this information, and he kept all these newspaper clippings. But the third one down is from Jessica McClure, the young 18-month-old that fell into a well in Texas. Those of you who remember, I think that was in the mid-90s. It was covered live on CNN for over a day, I think, and they dug her out and she was fine. She's a mother of 3 today, but some people aren't so lucky. They fall in a well, and a number of people get killed that way. Okay, so aquifers versus aquitards. An aquifer is, it's the unit where you're getting your water from. And in my field as a groundwater hydrologist, an aquifer can mean different things to different people, or what is it an aquifer, it might not be to another. So for an example, if you have a home and you need to pump 5 gallons a minute, you might be able to put your well in a specific geologic unit that'll pump 5 gallons a minute. But a community that needs a 300 gallon minute per well may be nearby and cannot put their well in that same unit. And to them, it's not an aquifer that's usable for community water supply because it won't pump 300 gallons a minute. And so that's where this definition came from. It's kind of convoluted, but it's really, there's a sufficient quantity of water from that geologic unit. And so an Aquitard is one that does not provide that. And so again, one person's Aquitard might be another person's aquifer in the end. But even, glacial till, we were talking about large diameter wells, those are not aquifers, but people still get water from them if they have a large diameter well, because it seeps in just enough to allow them to store their water in their large diameter well and use it when they need it. So yeah, enough of that. So whether it's confined or unconfined, so an unconfined aquifer is one that's really not full. It's got a free surface, so it actually has air. It's open to the atmosphere. And so the water table, whether it's an aquifer or not, is such a thing. And it's considered a water table aquifer versus, both examples I used of those wells, the water level in the well came up above the top of the aquifer. That means it's confined. It's under pressure. So the pressure in the aquifer is greater than atmospheric pressure. And so how far it comes up in the well is a matter of, the extent of the aquifer and where that pressure is coming from. So you can think of it like a juice box. If I put a straw in a juice box, nothing happens if I'm just holding the juice box. But if I squeeze it, then juice shoots out the straw. And that's what a confined aquifer is. There's external pressure somewhere away from your well that's causing the water level to rise in your well up above the top of the aquifer. And that likely means that there's a recharge area somewhere farther away where the water levels are higher, because water wants to be flat, right? You think about water in your bathtub, it's all one flat surface at the same elevation. If you pull the plug, water starts running out. Where's all the water run? It runs to that low spot. So it's the same thing as if your drain were a well that you're pumping. As you pump water from your well, all the water surrounding it's running to it to try to make it level again. And so when you have a confined aquifer, it means there's higher pressure somewhere else. So when you punch a hole in that aquifer where you're at with your well, water rises up into the well to make that level again. So it's coming up to the level of wherever the pressure is somewhere else. So another term for that is artesian. That just means there's pressure in the system. Artesian doesn't mean it's flowing out the top. It can be, but that's a flowing artesian well. And artesian simply means that the water level in the well is higher than the top of the aquifer. Okay, so as an example, here's a water table aquifer. This is all one unit. All this, the yellow at the top is the same as what's below that's unconfined. It's just that's where the water table is. And that's where the water level in the well is. Now, if we put in a confining layer, now there's two aquifers. There's the unconfined aquifer on top, and then there's a confined aquifer below. And the water level that well rises to, which you could see the dashed lines, it says potentiometric surface, that's the elevation of the water in the well. And that's caused by pressure from the sides, somewhere away from the well, pushing water up into the well. And because it's completely confined, and it's completely full. And so it's a pressure response, kind of like the juice box example I gave. And so you can have, if you have an aquifer that's confined, like that's what this blue one is here, the upper unit near land surface can have its own water table. So if I took a shovel and started digging, I might get 5 feet down, 7 feet down, 10 feet down, and I'm going to hit water. It's just where the ground becomes saturated, whether it's clay or sand or whatever it might be. That's the water table. And in this example, the aquifer that's below has, where that triangle is the water level. It's below the water table. So there's, when the water level elevations are different, water is moving from higher to lower. So it's moving down towards the aquifer through the clay material because there's higher water pressure in this top aquifer or top unit than there is in the aquifer itself. If it's the other way, so now the pressure on the aquifer is higher than the water table, then slowly water is seeping up, vertically up through the top of the aquifer very slowly because it's an Aquitar and it's separating them, but there's a net flow out of the aquifer towards the water table. And then you can have a flowing well if there's that much pressure. And that's just, you know, in some states like Michigan, they actually have a law that requires you to cap a flowing well and use a special type of cap so that it can't flow. There's a great book that we link to on our website called the Michigan Flowing Well Handbook that explains all that if you're in an area where you might have flowing wells. We have a few small areas in Illinois and in a number of states. There are areas where just the way the geology is laid out and the elevations and where the recharge areas are for some aquifers, you can have these flowing well situations. So we're updating this figure because it's really poor, but I'm going to use it. I use it today. So the example of that is if you look on the far right, it says recharge area for Artesian aquifer. So where those three arrows are between those two lines, that is one geologic unit, and you can see it comes down and then kind of flattens off on the left side. That's the Artesian aquifer. And what the dashed line is showing you is the potentiometric level or the water level in wells that are in that aquifer. So we have a flowing artesian well because the land surface dropped far enough near the stream that the natural water level in that aquifer, that artesian aquifer, is higher than the well. So you're gonna have a flowing situation. There's also a water table aquifer, and here's where these lines are, the line that right by the word water table, and you can see this short well that's a little grayed there where there's water in it. That should also be a dashed line. That's the water level in the shallow aquifer, and it's lower, right? And so the water level in the artesian aquifer in a well is higher than in the water table aquifer because of that recharge area that's off to, that could be 50 miles away to the right. And that's how a natural groundwater system works. And so that upper confining bed between the two, slowly water is seeping up from the artesian aquifer up into the water table aquifer because the net pressure is vertically up because the water levels are higher in the artesian aquifer. Good. So I hope I haven't confused everybody. But that's, you know, if you have more than one aquifer, that's what you see. You use water levels in wells to determine flow direction. You also have differences as you move, you know, laterally down an aquifer, up an aquifer, whatever. And when you move in any direction, water levels can go up or down by a little bit. That's why when we measure water levels, we also determine the elevation of the top of the well. And so then we make all those absolute measurements based on mean sea level, and we can tell flow direction from that. So if, you know, the artesian well that's on the right is at 690 mean sea level, and if we had another well on the other side of the stream somewhere off this picture, and the water level was 680 mean sea level, then we know water's moving from right to left in that aquifer because it's trying to be level, and it's not because of discharge areas or this flowing well could even has an impact. You can see here how the dashed line drops down. And so it's all moving through the system. It's recharging on the right here. Somewhere off this page to the left, that artesian aquifer is discharging, or it's connected to a shallower unit, or there's another stream, so water's moving through the system from right to left in that artesian aquifer. So here's an example in the real world. The St. Peter sandstone and the Ironton's Galesville sandstone are near the Chicago area. If you go far enough west towards Rockford, Illinois, they come close to the surface, but because of pumpage, we've reversed the flow in these aquifers because Elburn, Geneva, Elmhurst, and Bellwood all pump from these aquifers. That red dashed line is the actual water level surface, the potentiometric surface. And there's more pumpage in the middle of this image. And because of that, water is actually flowing as just like the arrows show. It's flowing into the middle both ways towards those wells. And so it's basically reversed the flow direction on the right, and it's coming towards the middle of the picture. And that's what can happen when you pump a well. And so you have to measure water levels to understand what those are, and that's why these diagrams are both in elevation. That's elevation of the water as well. And so yeah, that's how it works. So when you pump a well, what happens? I mentioned that water has to come back in to fill it up, and how fast that happens is based on the porosity and the permeability. So what we have here is we have two views. The top view is if you had a slice through the side and you're looking at a well that's somewhere in front of you and you're down in the ground looking at it. So when you're pumping the well, you see the drawdown is the darker blue to the light blue. And so you've kind of dewatered right near the well some of the water table where the dashed line is. So the other view below is if you're looking down on it from above, and those are elevation lines. So on the edges of the picture, the top picture, the water level is at 460 mean sea level. At the well, it's at 400 mean sea level. So if this were a perfect sand that was perfectly uniform and extended in all directions equally, you get perfect circles because water's flowing towards the well radially from when you're pumping it. And how much this goes down depends on what your pumping rate is. I mean, whatever this pumping rate might be, if you halved it, then the drawdown would be much less. It might be down to 430, and these lines would all be there'd be half as many lines, and it'd be twice as distant from each other. And how you determine that, I mean, you can measure water levels in other wells nearby, but knowing the aquifer properties, you can estimate what's going to happen, especially in a large production well, which this is meant to describe, because it shows 60 feet of drawdown when you're pumping, so this is a large pumping. So that's an ideal case where there's infinite aquifer in all directions. If you have two wells, there's not as much water in between them, so it draws that down more, and it's drawing more water from both sides from around it, or it's not just from each side, but also into the screen and out of the screen, which you can see that if you're looking down on it from above in the bottom half of that. And so you have very similar drawdown in both wells, and they influence each other. And so communities, large communities, can't put their wells too close together or they'll interfere with each other and there won't be enough water. So there's specific distance they need to be depending on their aquifer properties, how far apart those wells need to be so that they don't influence each other or restrict each other from pumping what they can. But it causes a larger and a much different shape cone of depression. And you can see what's dewatered near the top there, where it's the lighter blue. That was all saturated before those pumps kicked on, and now it's that water's gone. It's being pumped out of the well. If you have a boundary, you're near the edge of an aquifer, then there's not as much water to fill back in from that, further away, and so you'll see more drawdown. If you're too close to the edge, you may have limits on what you can pump. And so this is an example of when you get to the edge of an aquifer, that water is just not there. This is meant to be a bedrock below. And so a lot of large sand and gravel valleys have bedrock underneath them. A good example, we have a large sand and gravel aquifer that's an ancient bedrock valley river called the Muhammad Aquifer in Illinois. In places, it's 12 miles wide, and it's 200 or 300 feet deep. So it's really not much different than if you think about the Grand Canyon. If the Grand Canyon were full of sand and buried, All that sand is what we're getting our water supply from. And when you get to the edge, all of a sudden you're at the edge, right? There's no more sand, it's all rock. And so that's what this example kind of shows. It's called a barrier boundary. And now on the opposite side of that, you have, if you have a river that's connected to where your aquifer and your water are coming from, it's kind of like an infinite source. You can't pump enough if it's a large river, like the Mississippi, to influence with one well the water level in the river. So it acts basically as a constant elevation head, and it's always at 445 in this example. And so if there were no pumpage, it'd look like the picture from above on the right side of the river. Water's moving towards the river and the aquifer and discharging. That's the discharge point for this particular aquifer. But now that you've added a well on the left side, you see this cone of depression. And it's very minimized between the well and the river because there's so much water available. And so all of those things matter when you have a well, and understanding where you're at. You see a lot of folks who, buy this 5 acres on a bluff overlooking some nice stream or a small river, and it turns out up on the bluff there's no water. And so they end up putting their well down in those bottoms along the stream. One, you have to be careful about flooding, but that's because it's all this sand that was the ancient river bottom that now is a prolific aquifer, and that's why the well's down there. So I'm going to show Illinois' example, but I want to make sure everyone's clear that there are a number of states that have this very similar application. I don't know if they all share it between the geological surveys, but there was a question today about Idaho, and I got online, and it's, their interactive map application is almost identical. It's very similar. And so through the Illinois State Geological Survey, we're sister agencies and we share information. They've put a GIS interactive map online so that you can look for your well log, which is really handy. When you go into it, you'll see all these, the blue dots are water wells. There's other things, there's bridge borings, there's other types of wells, monitoring wells that are other colors. But, and the background, that's all that, I'm gonna call it tan because I'm colorblind, I'm not 100% sure. That's the boundary of the Mahomet Aquifer. And so Champaign-Urbana and the University of Illinois are on the kind of on the edge of the Mahomet. It's and it's the water source for our community. The wells are west of town, but you can see all the wells that are actually out here. Lots of water wells. And so if I zoom in, this is the airport on the south side of town, and I've clicked on a well, and it says I'm looking at the second of 3 that are at this location. So wells are typically located by legal description in 10-acre plot. And so on a 10-acre plot of land, there could be, if you have acre lots, you could have 10 wells. And so sometimes they're on the same thing here. But I'm looking at the second of 3 wells. It says who the owner is, when it was drilled, how deep it is. And then if I click on the API number, which is the Geological Survey's nomenclature, numbering system, ours is different. You can see this, and it's a generated log from their database. So they've entered all of the geology and everything else. You can see some details. This isn't everything that's on the log, though. If you remember the log that I showed earlier, there's a lot of other information. To get that, you'd need to go to the actual logs themselves or ask for a copy from the water survey. Some of them, we're trying to integrate all this. We've scanned a lot of our well logs. And so for this particular well, the blue is also an image of this particular well's actual log that was filed. And so that brings you to this, which was filed in 1968. And this is the original log that we've scanned and have in our files. We have the paper record here too. So it's you can find a lot of information. Things that are important to understand are who was the original landowner when the well was installed. That's the best, because I'm fairly sure that the Shawneckleys aren't there anymore in all likelihood. That's it could be through 3 or 4 homeowners since then, and so you're not going to find it by any of the others. It's going to be whose name is on the log when the well was installed. And that's one of the biggest problems, is figuring out all the information. And a good thing I'd recommend doing is you can go back to old plat books, which should be in your county records, to try to find all the names of who might have owned that land. That's one little trick if you're trying to find that stuff. So I want to talk a few minutes about the private well class. It's 10 lessons. I want to show you just some of the basics of what we have. If you haven't taken the private well class, I certainly suggest you sign up. It's sent to you once a week for 10 weeks, each lesson. It's a PDF sent to your email, so you're on your own to read it, but it's a lot of really good information. For every person that tells us one a week isn't fast enough, another person tells us that one a week is way too fast. They're 6 to 10 pages each. They have diagrams and they show a lot of information. Yeah, and it's at privatewellclass.org. So when you go to our website, just click on Take Our Free Class. It'll take you to a page where you can sign up. For each lesson, like the first lesson is called The Science of Groundwater, we provide a lot of other resources from other folks. A lot of times they're extension or a regulatory agency or a university. And so that is more information that you can go through. So if the 6 to 10 pages that we put together don't really resonate with you, you can go and look at other information. So we included all of this. And I'll tell you right now, Lyle Raymond, excuse me, from Cornell back in the late 80s, early 90s, developed a number of documents that, they're just black framed and they have blue on them, 3-color, white, black, and blue, but they're really explanatory and help you understand some of the basics of groundwater. And so that's why we included them. And they're all available through their website. Okay, so we do that for all 10 lessons. So there's other resources you can go to. Like I mentioned, the Michigan Flowing Well Handbook. That's the first resource listed there under lesson 2. We also have webinars like the one we're doing today, Well Care 101, questions and answers about common questions for wells, among other things. So all of those are recorded, like this one's being recorded. And what I will say is, like the Well Care 101, we probably offer every 3 or 4 months. The first material that we're still going through today is similar, very similar to what it was the time before. But once we get to the questions, it's very different. It can be very different. And so a lot of times it's worth just going through those videos just to look at the back half when we get to the questions, and you'll see today when we get to that. So we do some common ones regularly. Once a year we do one on septic systems, and we bring in Jim Starbird from RCAP Solutions, who was a sanitarian for 7 or 8 years in Massachusetts working on septic systems. He answers all the questions because he is the man for that. He knows a lot more about them than we do. And so, but we do that once every July. I think this year's is on the 7th. You can look on our website. But it's really useful. Septic systems play a big role with water quality in private wells in some areas where they both may be shallow, and it's good to understand how it can affect your well. Every so often, the last time we did this was in October of 2020, a webinar on financing and funding options. Now, the truth is, a lot of people who are on private wells want to be and want their independence. They don't want the government to bother them, all that stuff. But there's also a lot of people who can't afford to spend $20,000 or $30,000 on a new well if has a problem or fails, or even $3,000 or $4,000 to replace a pump or more. And so the most funding options are for low-income families. And there's a program the USDA has, but we talk about all of that in here. We even brought the USDA guy from DC on our webinar, and he explained their programs. And there's a number of groups. Several of the RCAP regions provide those loans. They're low interest, like 1% loans if you have well problems. And first step, if you're interested in any of that, I suggest is you go to our website and you watch this video, because it'll tell you what's out there. And it talks more than just about wells. It talks about septic. It talks about abandoning wells, programs that are out there for sampling costs, all kinds of stuff. And so it's worth looking. And then we've done 2, I don't plan to do any more because we've already covered it, on lead. And for this particular webinar, we brought in a lead and private wells expert, Dr. Kelsey Piper. And she talked about a lot of the work she's done to look at lead on the East Coast and a number of states, and what you need to understand about your home if it's older than 2014, where you could have lead solder, even if you have copper pipes, or if you have a home that's before the 80s, that it's likely to have lead pipes itself. You know, not every home that has lead in the pipes or the solder leaches lead. It really depends on the water chemistry, and that's kind of the message, is you need to sample to find out and understand if you're at risk. So, because there's a lot of lead pipes out there that don't cause leaching of lead, while there's certainly a lot that do. We just need to get rid of all of them. But yeah. And for this, particularly for lead, we have a page we set up. It's just privatewellclass.org/lead, so that you can get to other sources of information, like you know, down there, the water filters for lead reduction. There's some good information on certified products, or you know, what, like the state of Minnesota, what they found to be effective for lead reduction. And those are usually devices that would go on your sink. And so, yeah, it's pretty useful. There's a number of, we call them, quote, training videos that are on a particular topic. How does my well work? How's my pressure tank work? You know, this is what do I need to know about a shared well? We see a lot of problems with people who share wells, from water pressure to not, you know, friends who are no longer friends because they had to spend $3,000 to replace a pump and they had no plan in place for that. And so it just talks about some best practices that if you're on a shared well, things that you can do to, one, be prepared for when you do have one of those things happen, you know, a common a bank account or whatever, to deal with shared wells. And again, as I mentioned, why does my well keep losing pressure? There's one similar to this called How Does My Pressure Tank Work? That's by far the most popular video we have. It's had over 400,000 views in 5 years. And, you know, that's because a lot of folks have pressure problems with their private water supplies. They either don't have their pressure tanks and their pressure switch set correctly, or they're sharing it and there's, you know, where the pressure tank may not be working properly. There's just a lot of things that can cause that. Or you have an undersized system if you have a 3-story house. Yeah, and it addresses some of those. These are all like 4 to 6 minutes long. We started a podcast last year, and so you know, we're trying to bring on folks kind of at the intersection of water and public health. So, for instance, Dr. Wolf is a pediatrician at Boston Children's Hospital who works a lot with folks who have special needs or issues, health issues related to that. And Margaret Martins, who runs the Water Systems Council, and you know, they're a partner on a grant as well. But it's about they run a program called the Water Well Trust, where they actually find partners and corporations to help fund replacing wells for low-income families or families who have run out of water. So that if you're into podcasts, there's been 22 or so of them done now. I recommend you take a look. The whole class is available in Spanish, so if you're a provider, like at a local health district or county health department, and you have a significant Spanish-speaking population, let them know about this. It's all been translated. And, you know, we had a young man who was a Fulbright scholar from Columbia here at the University of Illinois, getting his PhD in civil engineering, who saw this as an opportunity to, who was frustrated by some of the poor translations that are out there for documents. And so he took it upon himself to make sure that we provided something that would you know, be reputable and easy to understand, and not have some of those mistakes in it. So the goal of our program really is to help well owners understand why their well is important, why they need to understand how it works, so they know when there's a problem what that means. And, you know, the bottom line is to protect themselves and their family from risk. And so we welcome any comments anybody has. If you have any other questions down the road, we're going to get to the questions now. And so, but yeah, hopefully we've had over 10,000 people take the class, and most of the feedback has been extremely positive. And so it's worth you going through, in our opinion. So we did get a bunch of questions, as I mentioned. We can't answer them all. And I know, we always send out a notice the day before, and we had probably 30 more questions last night. We did not get to those just because we already had a lot of questions to go through. And so if you have any more questions today, I see we have 2 already, but Katie's monitoring the chat and the question box, and you can ask them through that. And what I'll tell you is that I will answer all the questions I can. If I can't, I'll ask you to send me an email, and I will find an answer from someone who can answer it and get back to you. Which is better, cement grout or chip seal? So that's irrelevant based on your local or state well construction code, because you have to follow what it says. But 2 states don't have well construction code. I wanted to mention that. But in the early 2000s, Nebraska did a grout study where they used clear casing, and they put that they could run a camera down and see what happened to the grout on the outside through the casing. And what they found in the end is that natural bentonite chips were by far the best choice for the grout to actually stay in the borehole and to seal properly. They found that some liquid grout didn't stay in the borehole and went out in the formation, or basically didn't fill up the borehole the way it should. And so I know we had someone from DHHS talk at our 2017 conference, and he mentioned we assumed most states would change their well construction code after that, and only 1 state did, Nebraska. Now I know New Mexico told me last year that they were working on changing their code to match this a little more, but really, you should all. It's you assume a well's properly grouted. That means that there's no way that could be the source of contamination. But what this study showed is that in certain geologies that may not be the case. So I would use chips. I know we do that for all our monitoring wells. We use natural bentonite chips, not the preformed ones. Those flake off and stuff as you're trying to get them down the well bore, but the natural chips, just like they are, that are odd shaped and stuff, those are the best to seal a well, or the annulus. How would I know my house's well water is good, and how can I better understand the filtration process and equipment? So for the first question, you need to test and understand if your well water is safe to drink. That's really the only way to be sure. And you need to so you need to test. And as far as treatment equipment, if you bought a house and already had treatment equipment included, hopefully they gave you the manuals for that. If not, hopefully you have the manuals. If you don't, you can probably find them online. You just have to do a little searching, but most manuals for almost anything now are available online. And WQA, which is the Water Quality Association, and they represent a lot of the companies that make home treatment equipment, may be able to help as well. They may even have some of those manuals on their website. But what I want to really point out is if you have any kind of treatment, you really have to maintain it and follow the maintenance procedures, whether that's a filter cartridge you have to change, or adding salt, or changing out a cartridge. If you don't, those things can become the source of contamination. If they'll clog up, fill up, they get bypassed, they can be a source of bacteria. Especially a lot of times you have a filter before RO, and that's so that your RO will work more efficiently. If you're not changing your filter cartridge, your RO is probably not working very well either, because it just can't. And so you need to. That's probably the biggest thing with treatment equipment, is you need to follow the maintenance schedule you're provided. And just, well, I can get 2 more months out of this. You start doing those things, and you may be, affecting your water quality and what you're actually drinking. What are the regulatory, chemical, and biological testing requirements for private wells based on population? And what tests are recommended even though these tests might not be required? Well, so the first thing, There are no regulatory testing requirements for private wells once they've been installed. So if, you know, in Illinois now, when you install a well, they have to pass a test for coliform, E. coli, nitrate, nitrite, arsenic, I think, and there might be one or two other things. But then after that, you're done. It'll never have to be tested again. Now, there are 4 states that require testing of property transfer. The one who's been doing that the longest is New Jersey, and the state lab actually has to collect the sample. They share it with the buyer and the seller. They have to decide between the buyer and seller who's going to pay for it, but nobody else gets that data, and that's meant to protect property values. But and there may be some local jurisdictions, like you know, a local health district in Connecticut, for instance, or a county in New York that may require sampling and property transfer. But you know, in Illinois, for instance, if I buy a home with a well, there's no requirement to test, and that's most states. And so, as far as recommended tests, I'm going to go through what we provide typically here, just because it's worth explaining. There's a number of questions about it. It really depends on your situation. You need to know what formation means, geologic formation your water's coming from, for natural contaminants. If there are any known contaminants in the area, are there any sources nearby? You know, a few months ago, we had a person who built their house on top of a landfill, and I just, you know, shake my head, and it makes my head hurt to think that somebody did that, actually. But you know, it really depends. You need to ask questions. So ask your local county or state health department. Oh, and I guess I didn't change this from the last time it was asked. I apologize, because it says in Louisiana, so someone must ask about Louisiana. But this is really applicable everywhere. You need to ask. And if you do have a program, like Texas has a well owner program, you know, we have us in Illinois, there's other states, Virginia Tech has a program, Penn State has a program. Talk to those folks at Extension, or the people who house your state's well logs. And I'll give an example of that in a minute, but it's, you know, if you Google my state water well logs, it's going to give you the agency that has all the water logs in your state. Water well logs in your state, and even ask around your neighbors, you know, if they've had any issues, if there's anything that's known to be in the area, somebody may know. You know, like for instance, Tazewell County in Illinois has high arsenic in the Muhammad Aquifer, and it's higher there than in most other parts of the aquifer. And so if you called the Tazewell County Health Department, they would say, yeah, you should test your well for arsenic. But that's not the case everywhere. You know, arsenic isn't in all groundwater or in all areas. And then you should sample for coliform and nitrate annually. So they're really easy to test for. It's pretty it's pretty cheap to do. And the whole point of testing, coliform doesn't cause you to get sick. It's E. coli that causes you to get sick. The reason we test for coliform is because if you have coliform bacteria, it means you very well could also have E. coli. And it means that there's a pathway into your well. The same with nitrate. If you have levels of nitrate that are above background levels, you know, 2 or 3 ppm, then it means that you might have a shallow breach in your well, or your well's not sealed properly at the surface. And so if you have either of those things, they indicate a pathway into your well. So many people think if I test for coliform and nitrate and they're both good, you know, there's no bacteria and my nitrate's really low or at 0, then my well's safe. That has nothing to do with anything else like arsenic or any other constituents that might be natural in groundwater. You do that, again, because they will indicate that there's a pathway into your well, and it's a reason to be concerned and look for what might be wrong with my well and my wellhead. So some other examples. This is Rhode Island, and you know, pretty small state. I think it's 30 by 40 miles or so. The little dots are where there were orchards that used to use arsenic as a pesticide, and they've identified all those with definitely with soil contamination, some with groundwater contamination, and so they've mapped all those. But the big splotch that's in the middle is beryllium, and I say this every time I show this map. I had no idea beryllium was a regulated contaminant through the Safe Drinking Water Act, and it has health effects if you drink water that's high in it, until I saw this map, because it's just not very common. We don't see, I'd never heard of beryllium being a groundwater issue before, to be honest. And so that's why you need to ask, because who knows, if you're in Rhode Island and you're in this area, you should definitely test for beryllium. You can look on EPA's website under the primary drinking water contaminants and find it. They'll tell you what the health effects are, what the levels have to be, all that stuff. But no one, I wouldn't have thought to test or even recommend to anyone that they test for beryllium. And I wouldn't include beryllium on a list that I was going to give people all over the country to test for, but I would if you're in Rhode Island. And so you need to be a little inquisitive and look up at resources that your state or your local jurisdiction might have and find out if these sort of things are a risk. Just like Massachusetts, their DEP has this website set up based on uranium and arsenic. You can type in your address. They've done enough sampling in the state that they know where, if you have a bedrock well, where it could be a problem. And so you type in your address, it'll say, yeah, you should test for arsenic, or yes, you should test for uranium, or you should test for both. So it's just a useful tool as a well owner that you can use to help identify things that you might not or might not need to test for. If it comes back and says you don't need to test for uranium, that's good, because that's going to cost some money to test for, right? And then more advanced, and we're seeing more states do these sorts of things. The Wisconsin DNR is the primacy agency for both public water supplies, and they also regulate drillers and well construction and private wells. And so they've put up this GIS platform where you can, I put in arsenic by county, and this is the results I got. Up in the upper right, you can tell it what you want to display. And so it tells me that near Green Bay, there's 3 counties where arsenic is over 21 ppb as on average for the wells that they've tested there. And so if I were going to move to Green Bay area and I wanted to buy a house out in the country with a well, I'd know that I want to test for arsenic before I buy that. And if it needs treatment, to work with the seller to remediate that and make sure that it was safe before I bought it. It wouldn't prevent me personally from buying a house with a well, but I would be more diligent about being sure that I tested before I signed on the dotted line. And that's our advice to well owners. Anyone who's buying a house with a well is it's buyer beware. You should get it tested on your own volition, not wait for the seller to tell you it's okay. Yeah. So here's what we recommend. Again, annually, coliform and nitrate, and then every 3 to 5 years, sample for this number of constituents. They help us understand, like zinc and cadmium if it's galvanized pipe, which also has lead. But having this suite of constituents really gives you a good idea of what the groundwater chemistry is. And, along with issues you might have. Just for instance, chloride and alkalinity and pH together can give you a good idea if your pipes are going to be aggressive or corrosive, or your water is going to be corrosive, and whether or not you should be concerned about leaching copper or lead and that sort of thing. And a lot of these things should not change. So, I have several monitoring well networks around the state of Illinois that I put in the 90s. And one of them is in the Mahomet, where we have high arsenic. There's one well, it's a 300-foot deep well, that always has low arsenic, even though all the others around it, the closest, they're maybe 4 or 5 miles apart, they're all in the 40s or 50s. This one well is always 2 or 3. And we sample it about every 10 years. And, it doesn't change, because the groundwater itself in a deep aquifer like that isn't going to change dramatically. And the reason it's good to do this every 3 to 5 years is if you have a significant change in any of this, your hardness changes, or the turbidity or the TDS or alkalinity change, or pH changes, that might suggest something's going on near the surface, near your well, or with your well. And it's allowed the water to change, the chemistry's changed because of something going on. And so it's always good to, for your own peace of mind, to understand those things. Okay, so should I test for VOCs? Oh, I didn't change the wording here. Okay, so the question was today about pesticide runoff and whether I need to be concerned. I apologize, because I've answered this before, but I wanted to talk about it. So I included it here and I used the old slide. Because there's so many types of pesticides out there, it's really expensive if you tried to sample for pesticides themselves. What I try to make clear to everybody is that, you know, we'd only recommend that you sample for all those pesticides if you had a real suspicion that your well was contaminated. You had some reason to believe it was. But if your well's properly constructed and sealed at the surface and is properly grouted, and you know, it's not a shallow, large diameter well, then it's likely that you don't have any surface influences. You know, if you're going to have surface influences, you'd see nitrate or coliform in most cases. And that's not 100%, but it's pretty accurate. It's really those old shallow wells that were a concern, or a well that taps, you know, you only have a well that's 25 feet deep and it's there's fractured rock at the surface, or, you know, there's geologic factors that matter, and depth matters, as well as how well your well's constructed. And so you need to look at all those factors before you consider whether you want to sample for pesticides. I mean, I understand peace of mind, and maybe you decide to do that anyway, but it, you know, I mean, and it's just in some cases, you could, you know, we see a lot of subdivisions and new developments that are backing up to farm fields, and maybe they have their own private wells. Depending on where the aquifer is that they're getting their water from, there may be no real risk of those pesticides getting into your well water or into the aquifer. And so that's what I would recommend is you know, you continue to test for bacteria and nitrate, and you understand your geology, how deep your well is, how it was sealed. You have your well log. It's a reputable driller. You can ask them, you know, any chance this grout wasn't held in this unit. You just do your due diligence. I don't think everyone needs to test for pesticides, or for, you know, even be worried about livestock stuff. If they know all that other information, they can make a more informed decision. How do major industrial wells in the aquifer affect shallow private wells using mostly surface wells? So I wasn't exactly sure what this meant, because I think they meant, you know, like a shallow surface aquifer. But we do need a lot more information to understand this. One, if it's a major industrial well that's pumping a lot of water, if it's in the same unit and it's hydraulically connected, then yeah, it could impact your well. We see irrigation systems that are pumping 1,200 gallons a minute, affecting water levels in some private wells nearby in certain parts of the state. It really depends on if they're in the same aquifer, what type of aquifer they're both pumping from. You know, we have an area that's highly irrigated. I mean, there's 2,000 irrigation wells in this one county that's all sand, and yet because it's all sand, they get so much recharge, and there's so much water available that we only see drawdown like 7 feet in that aquifer during the summer. Whereas in some other areas where there's a lot fewer wells, but it's confined and it doesn't get much recharge, we may see 40 or 50 feet of drawdown near the pumping well for a high capacity well. And so we need to understand all that to really make a decision or a judgment on whether it might be affected. So, because all that goes into it, right? How far away must be from septic system with your well? And I cut and pasted these, so I apologize. I should have wordsmithed that a little bit. So every state but two have well construction code, and those require that you meet all of the setback distances. This is the top half of the one for Minnesota Department of Public Health, or Department of Health, but it's a good diagram because it explains a lot of things that you should be concerned about. But as far as your septic, it really depends on your state. I think in Illinois it's 75 feet. In some places it's 50, some it's 100. Sometimes with sensitive soils, it may be more. They may have a 2 times factor you have to apply. I think it really, you need to look this up for your state to understand what those setbacks are. So, and in some cases, you may be on very small lots and you may have vulnerable geology such that they won't allow a typical septic system to be installed. I know one of the RCAP folks I work with in New York was explaining to me about all these homes along a lake where it's very vulnerable. They all have basically their own treatment systems that are advanced septic so that the water that's being discharged has already been treated and isn't a risk. It can be naturally discharged versus septic systems that, in a vulnerable geology or where it's not, doesn't have a chance to go through the soil and be broken down, can be a source of contamination. And so you just need to look that up for your state. There were a number of questions about wells and well construction, and we do have some of that information available through these short videos. And again, if I haven't mentioned it already, I mean, everything on our website is free to use. All these videos, there's no cost to signing up for any of this. Fortunately, we're funded through RCAP and the US EPA. And so there's just a wealth of information available if you just spend some time looking through all this stuff. But how your well works, one of the other questions I think, well, no, that's not the right, I thought I had that next, but I must not. So as far as parts of well and all those, I'm not going to go through that because we have that information available. And but I want to point out that there is a lot there. So someone had asked about the likelihood of drilling a successful well on rural land in the Idaho Panhandle. Is there a database? So I just Googled Idaho water well logs. I mentioned this earlier, and the top result was the Idaho Department of Water Resources, and they have a mapping tool like ours. And so it's further below. I just copied the top part of their webpage, but they have a find a well map, and I didn't use it, so I don't know how fast it is or how anything else. But I know there was a phone number associated with it, and so I would call them if you and they can either walk you through how to use this, or because I know it said, for instance, most of those logs have information like depth of water, how deep the well is, all those things you'd need to know if there are any wells in your area that match. And that's typically the best way to just determine whether you can drill on your property, is to take advantage of all the people around you that have already drilled and the success they've had. Because the same thing go in the opposite direction. We've had folks who have to haul water in the summer because all they have is a large diameter well and it goes dry. Either it's not deep enough, or because of the changes in our weather patterns we've had over the last 10 or 15 years, now they don't have as much water available. And so again, you should be able to do this for every state in the country, is Google your state water well logs and find the agency at least that deals with that information. If there's a crack in the casing, what is the likelihood of surface water infiltrating it? So is the crack above ground or does it go below ground, for one? Is it on an upland or could that area flood? A crack's bad regardless. How big is it? I mean, if it's an actual opening, then bugs can get in, things like that. If the crack extends down below ground, then anytime it rains hard, anything that infiltrates is eventually going to saturate the soil there, and you're going to have a chance for infiltration. The best thing to do is just to get it fixed. They can, if like a 6-inch PVC well that's cracked from the very top down, say 3 or 4 feet, they can put in a liner inside that and seal it to hold that in place and prevent that from cracking any further. It just really depends on your exact situation, but I'd find a professional to look at it and give you advice from there on. From there. How much should I budget for a new well? Well, so it really depends where you're at in the country. Also, how deep you're going. A lot of them charge by foot. What type of casing, whether it's PVC or steel, and aquifer type, meaning if it's a sand and gravel well or a bedrock well. And there's locally there's a lot of other considerations. So I had a colleague here at the water survey who just put in a 110-foot 5-inch sand and gravel well, and it cost about $12,000. I worked with a number of folks in California when their wells started going dry in 2012, and recently a well owner installed a 600-foot bedrock well, and it cost over $50,000, and that's typical for out there for a new well. But this person had a 350-foot well that went dry, and by the time they installed a new well, they were told they should go at least 600 feet because of the drought and dropping water levels in a number of the aquifers out there. We also, Katie actually called a bunch of drillers. We just went to the National Groundwater Association's contractor lookup page, and we picked, I think, 8 states. We just picked a random driller and called, and we asked for the same type of well, 200-foot steel well into bedrock, and what would it cost. And it ranged from around $8,000 in Missouri to over $40,000 in New Jersey. And I would say they're notably going to be higher now than they were then. What I learned recently, talking to some well drilling type folks, is that because of costs, gas, inventory, a lack of supply, most things are upwards of 50% higher now than they would have been a few years ago. So the best thing to do is really to contract a couple drillers that are near you and get an estimate. They'll understand from your location. They've likely drilled near you, and they know what type of well they're going to put in and how deep they're likely to need to go based on their own records from drilling in the past. But before I do any of that, I would take our class. I know someone asked in the questions today about what questions should I ask a driller. We answer that in our class lesson, and it's an involved thing. You should, if you're going to drill a well, you need to make sure that you've got a reputable driller and all those things. And so it's worth going through all that material and becoming more familiar before you reach out to a contractor to build a well. I mean, it's the cost of a car or more. It's quite an investment. So you want to make sure you have all your T's crossed and I's dotted. Some other questions. What questions should I ask my driller? I just mentioned that. What do I not know about living on a well if I never have, and I just want to understand groundwater and wells better? All those things. There's a lot of information in our class lessons that I can't explain all in today. You should go through the class and you'll understand it all a lot better. I guarantee it. Is there an ample? Okay, if there's ample water in an aquifer, is an open bottom well better than a gravel pack well? Well, an open bottom well means you just have a casing that stops. That won't work in sand because you'll start pumping sand. And so usually you only see an open bottom well that's bedrock in consolidated geologic units. Consolidated means bedrock. And so I'm not sure another instance where you would have this option. But you install a gravel pack around a well screen because it's uniform size based on the screen size. It helps protect from fine sand getting through into your water in your well. And so gravel pack is certainly essential with a screen. And I guess you could put a screen in a bedrock well, but then you're casing it all the way down. But I mean, that's not the question. But you can't really have an open bottom well in sand and gravel. We've talked about that already, about pumping sand and how that'll damage your pipes and your pump and everything else. And so it's usually not an option. It depends on the type of well you're drilling. Can you explain the difference between sealed and unsealed well? There's really 2 ways these terms are used. If properly sealed in relation to the well cap and near surface well construction, means it's sealed from anything getting in it. So a sanitary well cap with a proper gasket, it's watertight, it fits snugly over the well casing so that nothing can get in the well. That's properly sealed. The other properly sealed is in relation to abandoning a well. If you follow your state's guidelines for proper abandonment, where you put either clay or cement or a mixture inside the well, so that when you cut the well off 3 or 4 feet below land surface, because you're abandoning the well permanently forever, it's full of material that won't allow water through. And that's so that the bottom, so that things from the surface can't get in your old well and reach the aquifer. And so that's properly sealed or properly abandoned. And I don't know if there's another instance of that, but that's the two ways that I typically would use the term sealed versus unsealed. And so we still have two questions that folks have asked, so I'm going to pull those up real quick. The Miracle Google Docs gives us the opportunity to share those. Let me make that full screen and then enlarge that. Where are we going here? It would be here. Okay, so hopefully everybody can see those. First question is, does it damage a well pump? Does it damage a well to pump it dry? No, it doesn't damage the well, but it certainly would damage the pump. You know, most of those are water cooled if it's submersible, or if it's running, it's going to get overheated. And so the more you draw it down, well, that's kind of subjective. So, I mean, really the honest answer is no, it doesn't damage the well to pump it dry. It'll eventually refill, assuming there's, any recharge at all. It just means that you're out of water for a time, but it will damage your pump to let your pump run. And so that's what you want to avoid. How can I get a well log if I just got a new house and never gotten one? So I guess you're saying here that did you build a new house and they put in a new well? So it's possible if it's really new. Sometimes it takes a while for those to get through the system. So like in Illinois, you file the driller files a permit and a log with the county health department. They may hold that log for 4 or 5 months while they wait for other logs to come in, and then send us a complete package of all the wells they've gotten over 4 or 5 months, or could even be longer. And then we have a two-step process because we work with the State Geological Survey and we share those. It might take another 2 or 3 months before it's all entered in both systems and available online. So if it's really new, it could be that sort of situation. But what I would do is contact the driller. And that's one of the best practices. I've had people tell me, well, my driller won't give me my log. Well, when you sign a contract with the driller for something that expensive, make sure it's in the contract that they provide you the well log they file with the authorities, and a complete geologic log and the pump setting, all those things. And so, because if you don't, some drillers, most are more than happy to give you the log. They filed it, they work well with others, but there's a few who feel that that's proprietary information, and if they share it, it's going to give their competitors an opportunity to come into that same area and drill wells. So they hold on to it like it's gold because it's their livelihood. And if you were in that business, you'd probably see that a lot more than you would if you're the well owner. But you need to make sure that if you're drilling a well, that's what you include. And if you just moved into a new house and it already had a well, then you should look online, like we just talked about. If your state has those logs online, or if it's a local health district or county health department, if they have them filed, you need to know, take from your deed, your legal description, and call someone and have them help you from your state resource agency that houses all the well logs. So, but if you can get it from the driller, that's the best thing, and hopefully they would give it to you if they have it. I'm not sure about hydrogen peroxide. I know it's being used more. I don't know that that's, so if you have sulfur, then it's either coming from sulfate reducing bacteria, or it could be coming from other bacteria and biofilms that have built up in your well. Or it could be that you have, if it's a bedrock well, it could be just naturally occurring. But I've not used hydrogen peroxide. I would use regular chlorine. And on our website, there is under lesson 10, I showed the lesson 1 and 2 and all the extra documents that are available to kind of give you more information. Under lesson 10, there is a guide from the Minnesota Department of Health on how to shock chlorinate your well. I would use that. The one thing I do know though is those bacteria build up in layers and become biofilms, and sometimes you have to shock it several times, and it could be because they're natural occurring in groundwater that you have to go to a system where you're continually chlorinating your well if it's bad enough. And we've seen some of those cases where people didn't have a choice but really to continue to chlorinate their water in order to get rid of all that. So, there's a lot of advantages to hydrogen peroxide from the standpoint of what it breaks down into and all that stuff. But it's apparently a lot more difficult to use because it's so reactive, and I don't know enough about it. I'm trying to learn because to me it'd be a better solution. One thing you don't have to worry about with chlorine, though, is you hear about disinfection byproducts with chlorine. That's because that's with continuous chlorination. That could be an issue depending on your water quality. But for shock chlorination, it's not, because at the end of the whole process, you're going to clear out all the water in your lines and systems so that there is no chlorine smell anymore, and all that chlorine will be gone. And so certainly for shock chlorination, I'd recommend using regular 5% chlorine. How many feet per minute well pump would you need for a well shared between 3 homes? It's gallons per minute. And it depends, there's friction loss. And so you'd really need to figure that out based on the distance between all the homes, the maximum use you'd have, what kind of pressure you want. I mean, there's a lot to that. Certainly larger than 5 gallons per minute. And you're still probably, you're probably having issues already, I assume. But the pump size is only one thing. It's really your pressure tanks, right? Do you all have individual ones, or is there, there's just a number of questions there. We recommend you don't have shared wells, to be honest. And I get some cases this ends up being, a family and their grown children have 3 homes shared between them. But you're probably best off talking to a well contractor about the best way to set that up to guarantee you all have enough pressure, because that's typically the issue, is that somebody, pressure won't be the same at all 3 homes, and it's a matter of, somebody's going to get the short straw there when everybody else is using water. So if it can't keep up, and they do make, there's a new type of pump that basically it's on demand. So when the pressure goes down, it starts pumping more, and you don't use a pressure tank, or it's just a 1 gallon or 2 gallon pressure tank. I don't know if that'd work in this situation or not, but it'd have to be a pretty big pump, I would think. So, because you have to realize that when you go to a larger size pump, you're talking a lot more energy costs as well. So, not a great answer, but I would talk to a local contractor. The geological layers recorded in the well construction record are fascinating. Who determines the layers and how? Well, the driller does, and that's honestly an issue. We have drillers who are excellent and understand what all those layers mean, and we have some who have no idea, and they put drift or terms that don't make any sense, and so there's no quote regulation of that. But it's come a long way. Especially old logs are terrible in that respect. And so most drillers today have the wherewithal to provide good information, because they realize how beneficial it is to them down the road if they go back to that area to drill again. Yeah. So, but it's super important to us. You know, a lot of the work we do is related to looking at large aquifers or large aerial extent and how that's going to, you know, how new, you know, for instance, I looked at some ethanol plants that were being proposed and how pumping 2 million gallons a day from this one spot is going to affect all the wells in an area. And understanding the geology is the key to that, knowing how thick it is, if it's continuous, and well records from well logs are the only way for us to map all that. And so it's super critical to us that drillers do a good job there. So, and that's in Illinois. I can't believe there's any, I've not ever heard of a program to, you know, every driller should have some geologic knowledge, but a lot of them learn it when they first start out as helpers on a rig, and they eventually become the driller. So it's kind of handed down in a lot of cases. How can I assess the condition of the well pump? You know, I honestly, that's a question for a driller or a pump installer. You know, we asked, when Katie was calling those same folks 8 years ago, we asked them how long a pump should last, and they gave us anywhere from 8 years to 25 years. My colleague that just put in a new well, his well was installed in, I want to say they think it was installed in the early 50s, and he had the original pump until maybe 4 years ago, and it's a shallow pump in his basement, so it lasted, you know, 70 years. And so it really just depends, and how to assess the condition, I'm not sure. You know, pulling a pump is expensive. They should just work. They're a mechanical device until they fail. And that's not comforting, but there's no way to really know that your pump's gonna fail unless you, yeah. I don't know. Again, I'd talk to a pump installer just because, you know, I don't know if you start seeing things like more energy use, you can, if you had it where you could determine that or whatever. I'm trying to think of ways that you could assess that while it's in the well, but I'm not sure. All right. Thank you, everyone, and hopefully see you next month. Thanks, Katie.
Thanks, Steve.